Hello everyone, my name is Mengzhao Wang. I'm going to present the paper, A Comprehensive Survey and Experimental Comparison of Graph-Based Approximate Nearest Neighbor Search. With the prevalence of smartphones, surveillance devices, and social media apps, massive amounts of unstructured data such as images, videos, and audios are generated every day. IDC projects that by 2025, 80% of data will be unstructured. Thanks to the rapid development of deep neural networks, we can accurately describe unstructured data through high-dimensional vectors. Among them, vector search is a basic module. An accurate NNS is infeasible on a large-scale datasets because of its exorbitant time consumption. So, most research results to ANNS, which allows for a slight loss in precision, while yielding multiple orders of magnitude improvement in speed. According to the index adopted, the existing ANS algorithms can be divided into four major types: tree-based, hashing-based, quantization-based, and graph-based algorithms. Recently, graph-based algorithms have emerged as a highly effective option for ANS. A graph-based algorithm builds a proximity graph on this site. Any vertex represents a vector, and any edge describes neighborhood relationship between the connected vertices. During the search, we start from the set vertex and approach query target through the neighbor's axis until the termination condition is met. Why do graph-based NS algorithms need an experimental overview? Our motivation can be summarized as follows. First, lack of a reasonable taxonomy and comparative analysis of inter-algorithm. Second, omission in analysis and evaluation for intra-algorithm fine-grained components. Third, richer metrics are required for evaluating algorithms' overall performance. Last but not least, diversified datasets are essential for algorithms' scalability evaluation. In addition, taking into account the recent trend of applying machine learning to graph-based ANS algorithms, we include comparison of machine learning-based optimizations. We analyzed 13 representative graph-based algorithms from a macroscopic perspective and summarized the four base graphs they rely on. Specifically, we elaborate upon the inheritance and improvement of relevant algorithms, thus exhibiting diversified development roadmaps. Meanwhile, we analyze how an algorithm optimizes the base graphs, such as improved index construction efficiency, increased recall rate. And we also classify these algorithms based on the base graphs. We found that graph-based ANS algorithms follow a unified processing pipeline. So we break each algorithm into 7 components and analyze these algorithms from a macrocosmic perspective. For index construction, we can compare the similarities and differences of algorithms from the 5 components. That is, initialization, candidate neighbor acquisition, neighbor selection, seed pre-processing, and connectivity. As for search, we can key instead into the algorithms from seed acquisition and routing. For instance, from the table on the right, we can see most algorithms' routing strategy is best first search. Next, we designed the experiment to answer the questions that we have summarized above. Our experiment involves 8 real-world datasets, cover various applications such as video, audio, image, text. In addition, 12 synthetic datasets are used to test each algorithm's scalability to different dataset performance, such as dimensionality, cardinality, clusters. The compared algorithms include 13 representative graph-based ANS algorithms. For evaluation metrics, we evaluate some less commonly used indicators, such as graph quality, connectivity, and average query path length. But they have a crucial impact on index construction and search performance. We re-implement all algorithms by C class. They are removed by all the field, refetching instructions, and other hardware-specific optimizations. We search for the optimal value of all the adjustable parameters of each algorithm on each validation dataset to make the algorithm's search performance reach the optimal level. Then, the construction efficiency and index size are mainly affected by construction strategy, category, and dataset, such as PNG and RNG-based algorithms with N descent are efficient. Construction on audio is efficient. For graph quality, there are significant differences between different algorithms. Then we can see that the smaller the average audio rate, the smaller the index size. From the number of connected components, some algorithms ensure connectivity, while others do not. For search performance, algorithms capable of obtaining higher speedup also can achieve higher QPS. Then RNG and MST-based algorithms generally beat other categories. Higher graph quality does not necessarily achieve better search performance. Then, candidate set size controls the quality of the search results. The larger, the better, Barcelona. It affects GPU memory limitation. Query path length is the number of hops from start vertex to the end vertex. It affects SSD I/O number. RNG-based algorithms have the smaller memory overhead. We perform the component evaluation and a unified framework. It classifies which part of an algorithm mainly works in practice. We found some interesting phenomena. For example, dataset GRST 1 million, algorithms NSG versus NSSG. In terms of overall search performance, NSSG is better. However, in terms of their claimed major contribution, that is, neighbor selection, NSG performs better. For machine learning-based optimizations, in general, existing machine learning-based methods can be viewed as some optimizations on graph-based algorithms discussed above, such as NSG. ML-based optimizations obtain better speedup versus recall result at the expense of more time and memory. Finally, we give recommendations in different scenarios according to the previous experimental observations. We also provide guidelines for algorithm optimization from 4 aspects, that is, high construction efficiency, high routing efficiency, high search accuracy, low memory overhead. Based on our observations and guidelines, we design and optimize the algorithm. It surpasses the state-of-the-art algorithms in terms of efficiency versus accuracy trade-off, while ensuring high construction efficiency and low memory overhead. Some tendencies. First, it is worth noting that almost all state-of-the-art algorithms are based on RNG and MST. Second, on the basis of the core algorithm discussed in this paper, researchers are refining and improving graph-based algorithms via hardware, quantitative encoding, and distributed scans. Finally, to meet hybrid query requirements, the latest research has structured attribute constraints to the search process of graph-based algorithms. Some challenges. First, almost all graph-based algorithms are oriented to raw data. A possible solution is data encoding. Second, high index construction time. A possible solution is GPU acceleration. Finally, adaptive graph algorithms or components selection. A possible solution, machine learning-based optimizations. Okay, thank you for your attention.